into there and block that reaction from happening. So the first step to understanding biology is understanding the structure of the protein. And these are protein crystallography beamlines. You'll notice this beamline looks a little different. It's actually in this room, and you can probably take a look at one of the ones around there. The reason that these are in a room rather than in a vacuum chamber is that the protein samples are actually frozen crystals of protein. If you know technically what a crystal is, it's a regularly repeating array of atoms, right? Making a protein crystallize is actually extremely difficult because these are thousands of atoms in a super complicated molecule. You have to make that repeat over and over and over. So that's like a scientific field in and of itself, just making the samples. Once you get a protein crystal, you freeze it into a little chunk of ice, basically, and they need to expose that to the X-rays. Well, if you take a chunk of ice and put it in a vacuum chamber, it's just going to evaporate and fill the vacuum chamber. So you have to be able to bring the X-rays out into the air so the protein crystal can live long enough to take a picture of it. So basically the beamlines come into here, and at the end of the beamline there's a beryllium window. Beryllium is transparent to X-rays, and that separates the vacuum on one side from the ambient atmosphere on the other. And then they put the protein crystal right downstream of that and take the exposures. Well, I should say the protein crystal, and then a really, really fancy CCD camera that costs $500,000 downstream of that. That's how they collect the actual image. Protein crystallography in concept is rather simple, actually. You have this regularly repeating array of atoms. You shine in waves of radiation, X-rays, and the X-ray radiation diffracts off of the atoms inside the sample, and it either constructively or destructively interferes. Now some of you at least have done the basic Bragg's equation for refraction of light. What they do is put the sample there, and then they have sample holders that can spin the sample in all different directions, 360 degrees. And then they take snapshot after snapshot. And they look for diffraction patterns. We'll walk by one, they're not all that much to look at. Dark spots on a gray image. And then they back calculate where all the atoms had to be to give you that pattern. And for those of you who haven't thought too much about crystallography, simple analogy. So you know when you're driving by an orchard in your car, and you get that really cool optical effect, right? Lines, and then a narrower spacing and a narrower spacing at the angles. Well, you might imagine if you measured all those spacings, you could calculate where all the trees were to give you that visual, right? It's exactly what they're doing here, except instead of like keeping the orchard still and driving by it, they're standing still and turning the orchard around and taking snapshots. And they measure all those spacings, and they can calculate eventually where all the atoms are in one of these structures. And it's not really that easy. You can't do it by hand anymore. You can do it by hand for silicon or some simple material. But these involve a computer model, iteration of predicting what you think you're going to see, comparing it to what the model says, back and forth, back and forth. But eventually they get a structure. And then they figure out what it's doing, how to prevent it. I mean, if you look at these, you see 3 in a row that look basically identical. Those are definitely not identical at all. And this is, current up to 2012. These guys have been operating a long time, so it's at least 15 years solid. And this is one beamline of probably 5 beamlines here times 80 around the world, and they're still not even close to solving all the structures. Now,